So in the previous videos, we found local max and mins, meaning in the general area where something was the greatest or least possible value of the function. In this video, we're going to look at global max and mins, meaning the greatest values over the course of a function. So for any function f of x, it has a global minimum at p if f of p is less than or equal to all the values of f of x. So not just in its area over the entire course of the graph. And the same is true for a global maximum. That something is a global maximum if it is the greatest possible value over the course of an entire graph. So just so that we can understand what's going on here, let's say we had a graph or a function that took on the following shape. And so if we had a graph that had this shape, we would probably want to actually consider 4 possible points for being the global maximum or minimums. In this case, I would identify this point here as being the global minimum. And notice how that's an endpoint. That's different than what we previously discussed, where local max and minimums were where the derivative was 0 or undefined, or we called those critical points. However, in this case, the global maximum is at one of those points. So we've got down here our global minimum occurs at an endpoint, and our global max occurs at a place where the derivative is 0. So that gets us to an important note, that we want to make sure that we consider all points where the derivative equals 0 is undefined, or the endpoints, because those are our possible global max and minimums. So we're going to look at an example and see how we do that. So in this example, we want to find the global maximum and minimum for f of x equals 2x cubed minus 15x squared over the interval -1 and 6. So the first thing I want to note is we have endpoints now. X equals -1 and x equals 6 are possible global max and min. So we want to look at their function values as well as the function values where the derivative is 0 or undefined. So let's find those points. F prime of x would equal 6x squared minus 30x. And we want to figure out where that equals 0. Well, we could actually factor this thing out. So 0 equals, I could factor out 6x, which would leave me with 6x times x minus 5. And then setting each of those equal to 0, x equals 0 and x equals 5. So there are 4 possibilities. 1, 2, 3, 4. 4 possibilities for where the function could have its greatest or least value. So what we want to do is plug all those back into the original function. So now these are the places, these are the possible inputs. We want to look at the outputs and see what in fact is the greatest and smallest values. So I'm going to look at the original function f, and I'm going to plug in -1, f of 0, f of 5, and f of 6. My 4 possible places for global max and mins. And we're going to look at those values and see what they come out to be. So if I plug in -1, 2 times -1 cubed minus 15 times -1 squared, and we compute that, you'll get -17. If you plug in 0, 2 times 0 cubed minus 15 times 0 squared would give you 0. Plugging in 5, 2 times 5 cubed minus 15 times 5 squared equals negative 125. And plugging in 6, 2 times 6 cubed minus 15 times 6 squared is negative 108. And so we wanted to find the global max and the global min. The global max is going to correspond to the greatest possible function value. That would be this point here when x equals 0. When x equals 0, f of 0 equals 0, and that's our global max. So the global max occurred at a place where the derivative equaled 0. This f of 5 equals negative 125. That would be our global minimum. So when x equals 5, f of 5 equals negative 125. That's our global minimum.